which is a company building superconducting quantum computers. And in particular, I work on an area called quantum error correction. So what I want to do today is explain some of the ideas of quantum error correction and how we can do some fun things by designing qubits in a way that makes it all a lot more powerful. So to explain this, I've got with me some Lego pieces. Now, the way that quantum computers work is that they have qubits, and you can imagine a qubit as one of these Lego pieces. And if you put together lots of physical qubits, you can run a computation, but it suffers from errors because each of these physical qubits is very noisy. So to build useful quantum computers, we have to do quantum error correction, which means that you put together lots of these physical qubits to make a logical qubit, which is like an abstract version of the physical qubit. It's encoded on a lot of physical qubits. And so you can imagine one of these square Lego pieces full of lots of physical qubits as a single logical qubit. And the most kind of well-established way of doing this is to use a code called the surface code. So this is a way of encoding the physical qubits onto a logical qubit. And there are lots of reasons that people really love the surface code. One of them is that it's very resilient to noise, so it can withstand a lot of error on the physical qubit. And another is that it works with all the qubits being directly nearest neighbor with each other, which is a constraint that modalities like superconducting have, that the qubits can only interact with ones next to each other. So you can make these patches, but there is kind of a problem. So you can build up your logical qubits to be bigger and bigger and bigger. So let's say you start with one physical, then you have 4, and then you can make these patches bigger and bigger and bigger. And you have to make them bigger to reduce your error. And you can get that error as low as you like by making your logical qubits bigger and bigger. But then you've now got to control all of these different physical qubits to do a computation. So that gives you a lot of physical qubits to control. Now there's a fun approach to reducing how many of these you need to control using something called Erasure Qubits. So to do this, you can essentially take 2 physical qubits, but put them together so you control multiple modes of the footprint of a single qubit. And what this lets you do is essentially a encoding on the 2 qubits, so that the main type of error that you get on this joint 2-qubit version is an erasure error. And this kind of error is cool because it's detectable. So it has a little flag, a little thing when you have an error that you can detect. So what's the point of using these erasure qubits? I'd like to show an example of what happens when you apply these qubits to a certain patch that you've used the surface code on. So imagine that we have a surface code where we have 4 physical qubits used to encode your data, your logical qubit. Now, if you do the maths and look at what you can correct with this code, you can detect one error. So it's an error detecting code. If an error happens on one of those 4 physical qubits, then it will trigger the extra qubits, the ancillas, and then they'll flag that an error happened. And you'll know what type of error happened, but you won't know where it happened. You don't know which of these 4 qubits actually had that error, and so you can't correct it. To correct it, you would need to use a bigger logical qubit. But let's see what happens if instead of using normal qubits, we use these erasure qubits, which have the 2 qubits in one. If we build our logical qubit out of 4 of these erasure qubits, and then an error happens, then we can actually flag where that error is. So there's a trigger that tells you that the error happened on that particular qubit. So you know from the other ones what type of error happened, and then you know from this erasure which location the error happened, and then that lets you turn this error detecting code into an error correcting code. And when you apply this more broadly, you just use these erasure qubits for a bigger logical qubit, then what you find is that the threshold gets higher, so it gets more resilient to the physical noise of the qubits, and it also has a lower probability of a logical error because you get this bigger power to correct once you know where the errors happened. And that's the kind of idea, is that you can actually, so the way that you can build these qubits, for example, with superconductors, is you can carve out like extra islands and add extra components into the same footprint that there was before. So why stop at 2? You can actually keep modifying, keep redesigning your hardware to build more and more complicated codes kind of within the hardware. So you can think of adding more and more modes to your qubits, so it's not just 2 qubits in one, but many more qubits in one, and then using these different levels to have more advanced error correction abilities, so you keep making a more complicated, interesting inner code in your hardware, built into the hardware, and then you match that with an interesting outer code. And that's how erasure qubits help with error correction. Thanks.